Okay, I already mentioned that the multiplication rule for independent events in the last video. That if I'm talking about wanting to know the probability of A and the probability of B, like what's the probability that they both happen together, if it's independent, that's the probability of A times the probability of B, which gives us another way to check for independence, because if I check these probabilities, or if I know these probabilities and they are true, then I can say that it is independent. Okay, this is related to the general multiplication rule because this is the same thing as the probability of A times the probability of B given A, because if they are independent, then this and this are equal. Okay, this simplifies just like the general addition rule simplifies, because the general addition rule is the probability of A or B, which is the probability of A plus the probability of B minus the probability that they both occur. However, if they both occur, if they're mutually exclusive, then this is 0. Because if they're mutually exclusive, then they cannot happen at the same time. So that would be 0. So, this formula and this, the large formula, both of the general rules, the general addition and the general multiplication, are on the formula sheet. However, the specialized ones for mutually exclusive and for independence are not. So you just have to remember that if it's independent, then this and this are the same. And if these are mutually exclusive, then this and part will just be 0. Okay, what is the difference between mutually exclusive and independent? Where they do not mean the same thing, and oftentimes people confuse them. Mutually exclusive means that they can't happen at the same time, or they can't occur together. And independent means knowing one does not affect the probability of the other. So knowing the outcome of one event, or knowing the occurrence of one event, doesn't affect the outcome of the other. So these actually do not have a lot to do with one another, except for the fact that two events that are mutually exclusive are not independent and will never be independent, because if I know that they're mutually exclusive, that means that if one happens, the other can't. So that right there tells me they're not independent, because knowing that the first one happens means the second one won't happen. Okay, and independence is all about the fact that knowing one does not affect whether or not the other one can happen. Okay, so let's look at some different examples. For example, baseball. In baseball, a perfect game is when a pitcher does not allow any hitters to reach base in all 9 innings. Okay, historically, pitchers throw a perfect inning, an inning in which no hitters reach base, about 40% of the time. So to throw a perfect game, you need to have 9 perfect innings. So what is the probability that a pitcher throws 9 perfect innings, assuming that their performance is independent of their performance in other innings? So coming out 1 inning has no effect on the next inning. Okay, well, if 1 inning has no effect on the performance, okay, of the next one, if they're independent, that means the probability that they do all 9 innings is just the probability that he does it in the first one, times the probability that he does it in the second one, times the probability that he does it in the third one, etc., all the way to the ninth one. Well, I know each of these probabilities, and in this case, each of these probabilities is 0.4. So this would be 0.4 times 0.4 times 0.4 times 0.4, which would just be 0.4 to the ninth. And 0.4 to the ninth, in this case, well, in any case, 0.4 to the ninth is the same thing, but this is our probability. So the probability that a pitcher throws 9 perfect innings in a row is 0.00026. Okay. So, because these were independent, I can just multiply the probabilities. So if I look at this next one, okay, let's look at the first trimester screen. The first trimester screen is a non-invasive test given during the first trimester of pregnancy to determine if there are specific chromosomal abnormalities in the fetus. According to the study published in the New England Journal of Medicine, approximately 5% of normal pregnancies will have a positive result. Among 100 women with normal pregnancies, what is the probability that there will be at least one false positive? Okay, it's reasonable for us to assume that these test results between women are going to be independent. There's no reason for me to think that because Susie has a false positive, that that's going to affect Mary's results. So they're each independent. I can assume that. So if I want to find the probability of at least one, okay, notice I'm at least one. So among 100 women, at least one would be the probability that there was one, plus the probability that there was two, plus the probability that there were three, plus the probability that there were four, etc., 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 all the way up to 100. That's a lot of probabilities to multiply together. But thanks to my complement rule, I know that since all of those probabilities add up to 1, it's a lot easier to go the bottom way. Because anything that is, not at least 1 is 0. So the complement of this, the complement of at least 1 is just 0. So I can say that's 1 minus the probability that there are 0 false positives. Okay? Well, if there are 0 false positives, that means all 100 women are going to get a true result. Okay? They're going to get negative results because they have normal pregnancies. And so if it's not a false positive, that means that then it's an actual negative result. Okay? So the probability that there are no false positives is the probability that all 100 women are getting accurate negative results. Each woman, okay, if there's a 5% chance they're going to get a false positive, that means there's a 95% chance they're going to get the right thing. So that would be a 95% chance for the first one, times a 95% chance for the second one, times a 95% chance for the third one, on and on and on and on and on. So really, there would be 100 of those. So that would be 0.95 to the 100th. So if I say 1 minus 0.95 to the 100th power, that would give me the probability that at least one would get a false positive, which is 0.9941. So that's over a 99% chance that out of 100 women, at least one of them will get a false positive on this first trimester screen. This complement rule comes in very, very, very handy. And remember that anytime you see at least something, the complement of that is less than that. So no more than the one below it. Okay, let's look at the check your understanding on page 323. Number 1 wants to know the probability that one returns, the probability that one returns safely is 0.95. Okay, assuming independence, because we're going to assume independence, the probability that they're safe on all 20 would be 0.95 to the 20th, 0.3585. And number 2, no. Whether one is a college student and one's age are not independent, because far more younger people are college students than older people. Okay, what if we're calculating conditional probabilities? So let's say, we calculated we calculated probabilities with and by using the probability of B given A, but what if I need to know the probability of B given A? Okay, I can think about it in terms of the same formula. If the probability that A and B is the probability of A times the probability of B given A, then I can just solve this formula for and, this general multiplication rule that is on the formula sheet, for this, which tells me it would be the probability of A and B divided by the probability of A. So the probability that they both occur divided by the probability of the given. Okay, that is my conditional probability formula. It is included on the formula sheet. Okay, and it's related to the general multiplication rule by just dividing. Okay, just solve this for the probability of B given A. Okay, a very common way of losing credit is not showing work. You must show all of your work. It is super important. You are going to lose credit. It's awful to lose credit when you have the right answer. You must, and I'm doing it in 2 colors to emphasize this. Not to mention all capital letters and 3 exclamation points. You must show your work on all of these probability questions. All of them. Okay, now that I've emphasized that, let's look at 2 last examples. Okay, in an earlier example, we looked at the relationship between media usage and grades for youth ages 8 to 18. Okay, that was from the other video, from yesterday's video. So it says, what percent of students with good grades are heavy users of media? If we look back to yesterday's example, I know that the probability that a student is going to get good grades, which I called A, was 0.6566, because that was what we calculated yesterday. And I know that the probability that they are a heavy user and get good grades was 0.1092. I could calculate that from my tree diagram. So if I want the probability that they are a heavy user, given that I know that they make good grades, I would take this 0.1092, divide it by my given 0.6566, and that's going to give me 0.166. So there are about 16.6% of youth with good grades are a heavy users of media. Okay, let's also look at this example. False positives in drug testing. It says many employees require prospective employees to take a drug test. A positive result on this test indicates that the prospective employee uses illegal drugs. However, not all people who test positive actually use drugs. Suppose that 4% of prospective employees use drugs The false positive rate, so that means people who get a positive on the test and actually don't do drugs, is 5%, and the false negative rate, people who do drugs but get a negative on the test, is 10%. What percent of employees will test positive? Okay, so this is not anything sequential. So let's make a two-way table out of this to help us organize ourselves. And I'm going to make a new page so I have plenty of room. Okay, so because this provides us with some conditional probabilities, it's usually easier to make a tree diagram, even though it's not necessarily sequential. Conditional probabilities usually work well with a tree diagram. So they either do drugs or they don't. And then they either get a positive or a negative, positive or negative. Okay, in this case, I know that 4% of prospective employees do drugs. So this would be 0.04, which means that 96% don't. And then I know that the false positive rate is 5%. So they don't do drugs, but they get a positive. That's 0.05, which means this 0.95, because these two need to add up to 1. And I know that the false negative rate, which means they do drugs, but they get a negative test, is 10%, which means that the do drugs and get a positive test is 90%, so 0.9. Okay, and I can find out the ands. This one is the probability that they do drugs and get a positive. 0.90 times 0.04, which would be 0.036. And I do the multiplication for this one, and I get 0.004. I do the multiplication for this one, and I get 0.048. And for this one, I get 0.912. So if I want the probability that I want to know the percent of people who test positive. Okay, well that's going to be the percent of people who do drugs and test positive, plus, because it's or the percent of people who don't do drugs and test positive. So these values here would be 0.036 plus 0.048. Remember, the percent of people who actually test positive is 0.084. Okay, the next thing I want is the probability that they do illegal drugs given that they tested positive. So what percent of people who test positive actually use illegal drugs? So that's asking for the probability that they do drugs given that they tested positive. So I'm going to use my conditional probability rule, which is that they do drugs and they tested positive, divided by the probability of the given, which is positive, that they tested positive. I know this one because I just follow my line, 0.036. And I know this one because I just figured it out, 0.084. And when I actually do the division, I get 0.429. So only about 43% of the people who test positive actually take illegal drugs.